Okay, this will be our last video for Chapter 2 on derivatives for Math 1560, Calculus 1 at U of L for fall 2017. And in this video, we're going to look at the derivative of the inverse secant function. Now, the inverse secant function is a little bit trickier than the other inverse trig functions. We looked at sine, we looked at tan. There, we saw kind of nice intervals that work, and when you get to the inverse secant function you run into a bit of trouble, and let me kind of show you what goes on. So first of all, here's the cosine function, right? We all know the cosine function. How do we define the secant function? Well, remember, secant is what? It's 1 over cos. So here it is. Right? Notice that wherever cosine has a 0, secant has an asymptote because you're dividing by 0, so it's going to go off to infinity. Right? 1 over 1 is 1, so you can see that the two graphs touch anywhere that we get either 1 or minus 1. So everything is fine there. But again, we see that the secant function, as you would expect, it repeats. It's not 1 to 1. And so if we want to define an inverse, how are we going to do it? Well, this one is a little bit trickier, and in fact the graph that I'm going to show you on here is not actually the graph that we want. It's not the correct graph. GeoGebra doesn't actually have an inverse secant function built in. You might be able to see over here that what I'm really doing is the inverse cos of 1 over x, right? That reciprocal relationship between cosine and secant lets you do this. The problem is that the definition of the inverse secant function that we want for calculus doesn't quite match up with what you get if you take this. So here's what GeoGebra gives you for the inverse secant function, right? So notice that what you have here is that this part of the secant graph, this first quadrant part, right, where our angles go from 0 up to pi over 2, it gets reflected and becomes this part here, okay? And where does this part come from? This part here, well, that's coming from these angles here between pi over 2 and pi. That gets reflected across and becomes this. This turns out to not be the definition that works well for calculus. It turns out that what we really want to take is, we want to take, for the negative part, we want to take this half going from pi down to 3 pi over 2. That's the better one to take for the inverse secant function. You'll see why when we calculate the derivative. So let me jump back to our slides. Okay. So when we restrict this domain of the secant function, as I just said, you take the first quadrant angles, but rather than taking the second quadrant angles, which would be a reasonable choice, and that is a choice that you would see in a lot of pre-calculus books, trig books, you would see that, and from a trigonometry point of view, it's the right choice to make. But from a calculus point of view, it's actually inconvenient, and so we prefer to take these third quadrant angles. I'll give you a hint as to why. The reason is that in the third quadrant, the tangent function is positive. We'll see where that comes up in a few minutes. Okay. So the domain is everything except for the numbers between -1 and 1, and the range is angles in the first quadrant and in the third quadrant. And as usual, we have this inverse relationship here, right? Secant of y equals x. Okay, so let's try to take the derivative. So let's rather than g of x, let's just call it y, right? Where y is the arcsecant function, secant inverse of x. Okay, so secant y equals x, and we're going to take the derivative of both sides. Okay, so remember that the derivative of the secant function, we calculated that one in class, I believe. It's secant u times tan u. So we get secant y tan y, but then we have to multiply by the derivative of the outside, or the inside rather. We have to multiply by y prime, and we get 1 on the other side. So I can solve for y prime. I get 1 over secant y tan y. So far so good. What do I know about secant y? I know that secant y equals x, right? That's how we basically define things here. So what do I do with tan y? Well, again, I use the fact that 1 plus tan squared y is equal to secant squared y. So tan squared y is, so secant is x, so this is x squared minus 1. And so again, if I want to calculate tan, right, I have to take square roots, and initially I have to take either a plus or a minus. And what you have to kind of be careful about here is it turns out that if you had defined things differently, if I had taken angles between minus pi over 2 and pi, rather than going from pi to 3 pi over 2, what happens is that when we're in the first quadrant, secant and tan are both positive and everything is okay. So essentially when x is positive, everything is positive. But when x is negative, tan is negative, and then you actually get a negative times a negative, and it turns out that y prime is always positive. And then you would have an absolute value. You'd have to put an absolute value function in. But because we chose to have secant have the inverse secant function take values in the third quadrant, if y is in either the first or the third quadrant, tan is positive in both of those quadrants. And so I can take the positive root, and that means that I get this result. The derivative of arcsecant x is 1 over x times the square root of x squared minus 1. And we're done. So that's it for chapter 2, and in the next series of videos, we'll start putting those together next week. We'll be talking about how derivatives affect the graph of a function. That's chapter 3.